Well, good afternoon, everybody, and welcome to the last session of our seminars for New York CBC. It's somewhat hyperbole to say that this man needs no introduction, but this man needs no introduction. And I've also been told that Matt Roselle wrapped his entire modern introduction of somebody else, and so I feel like that's a lot of pressure to go up to. But we're all here to learn a little bit about oxygen with Rich Michaels. And Rich brings over 30 years experience in brewing process control, fermentation science, and production organization. As the founder of I Make Beer LLC and co-owner of Second X Spirits, he helps beverage makers turn great science into great beer and produces award-winning spirits. He's a graduate of Siebel and has worked in both large and small breweries. And as I was quizzing him about his career, he mentioned that he had moved out to Michigan to work on a little startup that was called Founders Brewing Company, which I thought was pretty funny to refer to that as a little startup at some point. With that being said, I will get out of the way, and nice round of applause, please, for Rich Michaels.
Thank you. It's great to see we got people here at 4 o'clock on Friday. That's impressive. Might be because you need a nap after some cocktails or beverages upstairs, and that's okay too. We're talking about oxygen in the brewing process today. It starts early on, and we're going to talk more about packaging a little bit later on. Feel free to ask any questions anytime. Just raise your hand, yell, say, hey, you, whatever. Except for you, Dean.
Sorry, I'm late.
There's always one. So why oxygen matters? Flavor stability. We want to put beer out that tastes the same when the consumer gets it as when we put it in the package. Yeast health. Yeast needs oxygen as part of its life cycle. Yeast also produce a lot of flavors because of oxygen and amino acid take-up early on in fermentation. That lag phase is very important. Without oxygen, that doesn't happen. Shelf life. Like I said, we want to put beer on the shelf that consumers know what they're expecting and know that it's always going to be the same every time. And aroma production. We're talking a lot of time at this point about hop aromas, and there's talks on thiols and genetically modified yeast and all sorts of interesting, cool things. Those hop aromatics are still very fragile, so it's very important that we treat that beer properly so those aromatics make it to the consumer. And head retention, believe it or not, oxygen can impact head retention in beer. Foam positive proteins exist in hops, and as they oxidize, not so much. So your beer's not going to look as pretty, it's not going to taste as pretty, and it's not going to smell like you want as well. So what's important for us is dissolved oxygen. We'll look at that in several cases. As far as oxygen dissolving in product, cold liquid can dissolve more product than warm liquid. We all know that from carbonation. It's much easier to carbonate a cold beer. It's also much easier to dissolve oxygen in beer at low temperature, and hot holds less. The downside of that is cold slows oxidation reactions, and hot accelerates them. So we keep that in mind through our process. So one of the biggest things we can do is store finished beer in cold. And that means storing it in your cooler before you ship it, and then working with your distributor to make sure it stays cold as long as possible. You should also expect your beer to be stored warm and left in the sun at the retailer, because eventually that's going to happen to it. So we'll talk about hot side aeration in the mash, kettle, and whirlpool. There's not a lot of opportunity to dissolve oxygen in this part of the process because the liquid's generally hot. But we can get oxidation of lipids in malt, which will lead to trans-2-nonenal. I know there was a flavor class earlier here today. I think they probably had the Siebel kit, so T2N trans-2-nonenal was probably part of that class. Anybody ever experienced that before, that stale papery flavor in beer? How many people have experienced that in the wild with beer that they've purchased? Anybody? I know some people have experienced it in class. Anybody do it in a sensory class at all? Yeah, it's a good one to learn. So what's important here, we have to look at mash handling and lautering. What can we do to limit air getting dissolved or oxygen getting entrained in our process? So we want to look at avoiding splashing when transferring wort. That's our biggest opportunity. We're going to make sure we use hoses, and we want to fill vessels from the bottom. A lot of breweries, a lot of small systems tend to fill things like their kettle from the top of the vessel. That's nice, it prevents backflow, but there's also an opportunity to splash your water around there. So if you can figure out a way to do that safely with some hoses and check valves, that's an opportunity to improve your process. Or if you come into the vessel and are able to divert the flow down the side of the vessel, that'll help as well. The biggest opportunity I see in smaller systems is grant design. Who here has a grant on their small brew house? Are they open grants? No? Okay, closed grants, that's impressive. A lot of grants used to be open. I think you see more modern designs today where they tend to use closed grants. And you gotta make sure you keep that grant flooded. You don't want to empty that grant. You don't want the pump to draw a vortex and suck air into your process, because you're gonna go through that pump and it's gonna stir that oxygen, give you a lot of exposure, and increase your oxidation of your wort products, and you'll look for that stilling later on. You also want to minimize excessive stirring during the mash for a few reasons. Excessive stirring can develop beta-glucans, things like that, which will lead to slow lautering. It's outside the context of what we're doing here today. But if you're stirring so much that you're whipping air into your process, those reactions occur pretty quickly at hot temperatures. It's hard to dissolve too much oxygen, but just by the fact that you're constantly whipping that mash around, you can also cause problems. So, if you're stirring your mash, as you empty the vessel, maybe adjust your speed so you're not drawing a vortex and not splashing your mash up the sides of the vessel. And then make sure all your pump connections are secure and tight. If you have wort leaking out of somewhere in your system, oxygen is getting in. I guarantee it. I have worked at breweries that had a leaky hose clamp upstream, and you can always see that oxygen in the process. Well, no, that doesn't matter. Beer is getting out. It's not carrying oxygen. It is, trust me. We put meters on systems in breweries all over the world, and every chance you see beer coming out, or in this case, wort, oxygen is getting in. And like I said, in these cases, you're often going through a pump, which is also giving that an opportunity to stir more in as well. So during the boil, having a good vigorous boil is important. That drives the dissolved gases out. Like I said, high temperature, low solubility, and also you're driving air out of the headspace of the vessel. So as you fill the top of that kettle with steam, there's no air. No air is no oxygen. You're going to limit aeration there as well. So even on a very vigorous boil with internal calandria, you're going to see less oxidation because you're filling that headspace with steam, displacing the air in there. So you want to fill gently on the way to the whirlpool. A lot of people I know use pumps to whirlpool. If you can minimize pump usage, it's better for a lot of reasons. So you want to gently fill. If you're going from a kettle to a whirlpool right next door, start that transfer by gravity. Half of that transfer can be done with gravity. You bottom fill that vessel, you're not going to splash it, you're not going to spray it around the vessel. You'll limit aeration right there. And then as far as whirlpooling, everybody loves to whirlpool as fast as they can. There is no reason for that. 3 to 6 RPM is optimal for whirlpool to help in separation. In most cases, in a small system, you have a 5 to 10 barrel, even a 20 barrel brew house, you can whirlpool very effectively with a paddle without introducing oxygen, without creating shear forces. The whirlpool, we're looking to settle particles out of solution. As you go through that pump and high velocity, you're shearing the trube that you formed in the brewing process. If you can maximize trube size, you're going to get better settling. It's Stokes' law, particle settling. A particle twice the size will settle 4 times faster. So if you can minimize shearing of trube, that's going to help you in the long term. And trube and protein and all that will get into your process and can react with oxygen later on and create stilling reactions. So after we come out of the whirlpool, after we do our rest, we separate things nicely, nice and clean. We've got good clean wort, and you can measure that. There are ways to do that with an IMHOF cone inexpensively. Look for you'll settle something out in a graduated cylinder or something, you can actually measure how much trub you have. So what happens with yeast and oxygen? On the cold side, yeast produces sterols, and we survive on sterols. Cholesterol is our energy source as humans. So sterols are the yeast's energy source, and the yeast needs that to go ahead and continue on with fermentation to make our beer for us. As brewers, we make wort. Yeast makes the beer. Yeast also produce fatty acids, which help with the yeast to reproduce and produce new cells. That reproductive phase we go through develops a lot of flavors, and that helps the yeast stay healthy later on in the process, help things finish up in fermentation, go through diacetyl rest and things like that. So keeping that energy level high and keeping that cell membrane as strong as possible will help your yeast later on. Yeast growth, like I said, aerobic phase, amino acids are taken up, produce flavors. Those flavors are very important to beer. For example, wheat beer yeast, Hefeweizen yeast. We can manipulate that yeast by manipulating our oxygen level. A low oxygen level will produce more of that clove character that we expect and desire in wheat beers. If you over aerate a wheat beer yeast, you're not going to get any of that 4BG. So by manipulating our yeast and being consistent with that, we can control the flavor production in our beer. And additionally, everybody's worried about sulfites in wine and labeling and stuff like that. Fermentation produces sulfites. It's a natural process. Those are antioxidants. Lager yeast produce more sulfites than ale yeast. And by managing fermentation effectively with optimal oxygen levels, we can get that yeast to produce more natural sulfites, which are antioxidants, which will help our beer stay fresher longer in our process. There's some great work done by Eric Samp. He was a process guy at Coors. I think he's now at New Belgium. He wrote papers on how to manipulate yeast to maximize sulfite production. He was at Coors. They're making light beer, which would show oxidation, and they manipulated their process to build natural antioxidants in. As brewers, we don't need to label sulfites unless they're over 10 parts per million. So his focus is on optimizing fermentation process and aeration to achieve just under 10 ppm to give them the best potential shelf life. So oxygen targets for yeast and wort, we're looking at 8 to 10 parts per million, generally for ales. Lagers generally require a little bit more oxygen, 10 to 12 parts per million. And some high gravity products can be 14 parts per million or higher. Typically we do this in line on the way to the fermenter, and we want to put all the yeast in the first brew. I see a lot of people not know what to do when they get to the point where they're doing 2 brews a day. Do we put yeast in twice? Do we aerate twice? You don't want to do that. Oxygen goes into wort, yeast takes it up, does its thing. If we send yeast and wort to the tank once, and we follow it up with more oxygen, we're going to trick that yeast into going back to its aerobic phase, and we're not going to get a consistent result. So do it all at once, take care of it, everything on the first batch. And I've seen this done incorrectly at small breweries, and I've seen it incorrectly done at large breweries. But if you can control your aeration on your yeast in one shot, you'll have the best possible chance of being consistent. There's a newer technique. I was working at a brewery a few years back. We put a state-of-the-art aeration system in, amazing technology. Because of some circumstances, we had some construction issues. It took us a while to do that. We got done with that. Of course, the German brewing engineer who sold us the system said, "Why would you do that? You sold us the system." "Oh, we don't do that anymore. That's the old way." The newer technique is actually aerating the yeast, because that's where we want the oxygen. Not always practical, but that shows us the importance of taking care of our yeast more than putting oxygen in the brew. Putting oxygen in the brew, we're going to oxidize some products in our process, as well as provide oxygen for yeast to take up. A healthy dose of yeast, my experience usually takes up about 4 parts per million of yeast per hour. So oxygen goes away pretty quickly. That's why you don't want to be doing this multiple times. So also in multiple fill, we want to go through and try and get all of our wort in the vessel in 24 hours. Anybody here doing multiple fills in a fermenter? I know you guys are doing 9 at one point, right, Dean? Mm-hmm. Nine brews into a fermenter, but that was in 24 hours.
In one fermenter?
Yeah.
What's the size of the brew system and the size of the fermenter?
Well, that was back before they put the new brew house in. That was a 1,000-barrel brew house with 9,000-barrel fermenters.
Yep.
Same thing applies at 1 barrel, though. So ideally, we want to be able to measure oxygen. There was a good talk that Jim McDermott did 2 hours ago on process control. We need to measure this, ideally. An inexpensive optical oxygen meter for wort level ppm oxygen is only a few $100s. Something worth considering. So what do we do if we don't have that? How do we manage that? Well, like I said, do everything in the first brew. We can calculate the mass of oxygen if we know our flow rate in liters. We can do that math. We know how long it takes to transfer our wort. We can do how much oxygen do we need per hour, how many liters per minute. We can break that down mathematically and take care of that. And if you know your wort flow rate and your oxygen flow rate, you can estimate your parts per million, as long as you see that wort being dissolved in line. Let's put a sight glass right before your fermenter. A small rotometer, little oxygen regulator with a little ball in it will give you liters per minute. It's pretty easy to do. It might be liters per minute, it might be standard cubic feet per minute, but it's just math. It's converting from metric and back. So, any questions on that? Yes.
Do you have a favorite like DO meter for pre-fermentation?
I've used several. My personal favorite that I've experienced with is I don't think they make anymore, was the Hawk HQ 40D. That was a nice pH meter that happened to have you could pull the pH probe off it, put an oxygen probe on it. It was very versatile. And if you move the probe to another meter, the calibration stayed with the probe. I don't know what they currently do, but I believe that meter has been discontinued. So. But now I'm distilling, so I don't care. Yes?
Do you have a time and, rate of flow that you suggest for if you're airing the distillery itself?
Well, as Jim McDermott said, the expert consulting answer is depends. What's your flow rate? How soluble is your oxygen? What's your wort temperature? You have to put all those things in. You have to do some Henry's Law and do some math and say, okay, how much oxygen can my wort hold? How long is it taking me to get there? Also, people ask me about using oxygen versus compressed air. Compressed air is fine. You can achieve these numbers with compressed air. Food grade, medical grade oxygen is nice, but you can get there with compressed air. Make sure it's filtered, make sure the air is food grade, make sure there's no oil in it, all that good stuff. But it's pretty easy to do. Hey, Dave. So post-fermentation, what are our concerns? Out after fermentation, yeast takes up that oxygen, life goes on, yeast makes beer. We've got a tank that's basically near zero oxygen. At that point, we have to look out for staling reactions. We've got aldehydes that we don't want, and we see hop degradation. And in high levels of oxidation, we can see changes in wort color. That's very unfortunate. That means you've had a real bad day. And I've gotten those phone calls where, hey, something's wrong with my beer. We put it in cans, and it's really a lot darker in about a week. Well, it doesn't smell like hops anymore either. Well, how did you know that? Magic. Hops are the most sensitive part of the process here. What's that?
Then you just distill it and they...
Yeah, call me up and I'll redistill it and make something out of it. In the world of distilled spirits, things are a bit different. Some of the horrible off flavors that we taste for in sensory in breweries, like for example, butyric acid. It smells like baby vomit. It's horrific. Unfortunately, I judged for the competition this year, and there were a few examples of it. In distilling, those are not bad things. In distilling with long-term aging in wood and the oxygen process there, those will oxidize into pleasant flavors. Ethyl butyrate, which smells like pineapple. makes great rum flavor. Well, but that rum in fermentation, there was a lot of really nasty off flavors, but they later become pleasant things. That does not happen in brewing. I'm fairly new to distilling. I've been distilling commercially for a couple of years now. We've got a couple of gold medals. We're off to a good start, but I'd love to learn more about how those transformations happen. And right now in beers, for the last 20 years, we've had the Brewers Association, the Master Brewers Association for over 100 years. There's a lot of good information that you guys have access to. The distilling industry, not so much. A lot of stuff's trade secret there. They're coming around. Distilling at home is technically illegal, so there's not a lot of published information available to us. But in beer, you guys have access to a lot of information. Take advantage of it. So what we do in our process later on, closed loop transfers. If we can limit oxygen exposure, emptying a tank, putting hot pressure on a tank and not letting air into a tank, purging hoses. How many times do we hook up to a hose in that tank and run to another tank and not purge that? There's an opportunity there to purge that hose with beer or carbon dioxide or whatever. And then pump cavitations and leak, like I said, if beer is coming out, oxygen is getting in, usually at a high level. And pumps, kind of are rough on beer, so they're stirring that oxygen in. That's going to come back to haunt you later on. And oxygen is cumulative. So oxidation that happens in the brew house, plus oxidation that happens in transfers and fermentation, plus oxygen picked up in fermentation, plus oxygen picked up in packaging, those all add up. So the more, if you can solve some of these problems early in the process, you'll have more leeway later on. Dry hopping, this is a great source of picking up oxygen. Can we purge hop dosers with CO2 before we use them? Yes. Can we purge tanks and not just open a port on top and try and do a closed system? That's definitely better. There are hop slurry systems where you can slurry the hops up. Generally these work with some type of purging device. Very important. We can use a sealed hop doser that triclamps on a tank with purge ports. Do it. It's an expensive investment. It'll save you a lot of trouble. Like I said, transfer oxygen risk, air suction, seal failures, pump cavitation. If your pump's hammering away, that vibration and that high and low pressure surging is going to cause oxygen to get in. Clean in place. We use a lot of caustic to clean tanks, and tanks are, we've taken up all that CO2. Those tanks are full of air when we're done. There are opportunities to use things like acid cleaning. You can clean under CO2, under pressure, and not introduce oxygen to your process. There's challenges. Can we validate that CIP? Do we have sight glasses to look in the tank to see if the spray ball was spinning and things like that? Those are definitely concerns. You have to develop an SOP. How long do you feel comfortable using an acid clean without checking my tank? Maybe it's 3 turns. It's up to you. You need to validate your process and see where that opportunity is. Filtration, diatomaceous earth, filters. There's a lot of entrapped air in diatomaceous earth powder. Additionally, things like iron are often found in DE powder. DE is harvested out of the earth. They tend to pick up a lot of other trace metals. There is food grade diatomaceous earth, and then there's also beer grade diatomaceous earth, which is lower in iron. Membrane filters work well. They're generally closed systems, pressurized. Sheet filters do pretty good. You can get some diffusion on your sheet filter if it's not packed too tight, if you don't have it locked down really good. Again, pre-purge. If you're setting up a DE filter, if you can set that up with deaerated water, or even filter tap water and purge out with CO2, you're going to eliminate a lot of your risk. There's some breweries I know and work with will do some type of small antioxidant dose just to knock oxygen out of the filter when building it. Centrifuges, there's a lot of smaller breweries that have centrifuges these days. Larger breweries generally have them. Inlet turbulence, if you've got high shear forces, if your centrifuge is leaking, the internal seals in the machine, is the hermetic design or open design, depending on if it's one of the blue machines or green machines, depending on who manufactured it. Those are definitely concerns. And if you can make sure the flow runs continuously without starting and stopping, that will help. And oftentimes, I've done audits of breweries, we'll put an inline sensor in behind a centrifuge. And when the centrifuge discharges, if things aren't optimized, pressures and things like that in the bowl, you'll see your oxygen surge every time the machine discharges. It's like a heartbeat. It means the machine needs to be tuned. But if you put an inline measurement there, you can actually say, well, we need to talk to the centrifuge guy and see, should we seal this better, should we purge this better? There's definitely opportunities there. But it's very frustrating to see every time the machine goes, you see that level blip up. That's going to damage your beer. Bright beer tanks, CO2 pressure. It's important to maintain head pressure on tanks. A lot of people will start to purge a tank and say, well, the CO2 is heavier than air. That's somewhat true, but it's not a great way to measure or to guarantee your beer is not going to be exposed to air. If you do that and you fill the tank completely and push all the headspace out, you'll do better, but it's not a great effective way to eliminate oxygen. And you can purge tanks. Oxygen measurements in finished beer is at a much lower level. These machines get very expensive. In my experience, they start about $6,000. They go up to about $20,000 depending on the manufacturer and technology. If you're buying a $200,000 bottling line or canning line, invest in an oxygen meter. It's important. So when you start purging tanks, bright beer tanks, the higher dollar, the lower level meters can often be set to read gas phase measurement, and you'll actually go ahead and purge your tank and measure how well you purge your tank. Typically they read in parts per million V-bar, which is parts per million per volume, referencing barometric pressure. Just have a standard. And we purge till we see a certain number. Be consistent about it. And that's affected by the purge rate. If you purge very quickly, a very turbulent purge, it's going to take you longer to flush oxygen out. I do know some small breweries that will take gas coming off a fermenter and use that to pre-purge tanks. Probably a pretty safe bet, as long as you're not blowing foam out of the tank. Carbonation practices, purge your gas lines as needed. If your quick disconnect goes up to the tank, you're in pretty good shape. But if you have a shut off on the wall and your tank is empty sitting there and gas is emptying out of it and air is getting in your line, and you start using that line, you're going to be pushing oxygen into your process. Another thing is talk to your people who fill your bulk CO2 tanks. Obviously, you should be using food grade, beer grade CO2. But I've seen breweries, I've done audits where everything goes really well, except about every 12 days. Sometimes it's 14 days. What happens then? Well, the bulk company comes and fills their tank that day and doesn't purge their hose, and they blow a bunch of oxygen in the system. And that shows up in the beer. And we could actually, again, see that little heartbeat. You'll see a pattern there. So if somebody's delivering your CO2, most people I talk to say, well, the driver's supposed to do that. Just make sure they're doing it. It's not that hard, just ask. The squeaky wheel gets the grease on this one. Anybody here using deaerated water in the breweries? Two? Okay, that's good. So a lot of times breweries will use deaerated water for pushing beer, for flushing process, things like that. There's no air in that. And some breweries will also produce high gravity beers, then later go back and blend beer with it. We all had a couple of Utica clubs probably in the last 24 hours. That beer is brewed at high gravity and then diluted later on. So we were focused on making sure the blending water was real low oxygen level. So there's different technologies for that. There's membrane systems, there's nitrogen stripping. You can actually boil water in your kettle, cool that down, keep it sterile, and you're eliminating all your oxygen there as well. Again, verification is important. If somebody messes with your CO2 pressure or your vacuum pump, seals start to wear, all of a sudden your oxygen level is going to creep up. And if you're putting that in your beer, it's going to wind up in your process and your beer is going to suffer for it. So packaging, this is the highest risk stage for oxygenator process. We'll talk about dissolved oxygen versus total package oxygen, headspace oxygen, bottles and cans, and trying to maintain your filler. If you can keep your filler running and maintain a constant bowl pressure, things at equilibrium, your oxygen's going to wind up a lot better. So for bottles, we tend to do something called pre-evacuation. Bottle will go on the filler will draw air out of the bottle through a vacuum pump. There might be single pre-evacuation or double pre-evacuation, and that's going to lower, and you'll draw the air out, you'll flush with CO2, you may draw it out again, flush with CO2 again. That's going to reduce your oxygen in the bottle. It's important that you have timing done properly on those machines for that, making sure there's enough time to vacuum the bottle appropriately. I worked with a brewery a while back on a consulting basis. They had a filler that had a pre-evac filler, and they had a manufacturer that was supposed to build them a certain size filler, and the manufacturer said, "We're going to hook you guys up. We're going to add more heads to your filler so you can run faster." Now that shortened all of their pre-evacuations, and their beer suffered for that because they did not have proper pre-evacuation and CO2 flushing to keep oxygen low. It sounded great at the time. The guys in the office loved the idea. And in bottles, we want to make sure we cap on foam. We want to induce foaming in that bottle and put that cap and crimp it on and make sure there's no headspace there. We'll talk about TPO in a minute, total package oxygen. I sat on Jim McDermott's presentation. This is a great parameter to watch. This will give you some idea how effective and how in control your packaging system is. Can packaging, nobody does bottles anymore, so cans are the way. We can't pre-evac a can. If we draw a vacuum on a can, we'll suck it collapsed. So typically what we do is we'll pre-purge those vessels. And the important part here is flushing CO2 under the cover as we drop that lid in the can. We don't want to fill that can turbulently. We want things to be a gentle fill from the bottom of the vessel. I know there's some small fillers out there now that fill from the bottom of the vessel with long tubes without a sealed system under pressure. Those systems are going to expose you to more oxygen. There are small fillers that are, 12 head fillers, small rotary fillers that, you can achieve a great quality and keep your parts per million very low in your total package oxygen. It can be done. So we'll talk about headspace and TPO again in a second. And kegging. Keg washing and purging. Have a standard operating procedure. If you have a small manual washer, make sure you're optimizing your purging, making sure, this is an opportunity for acid washing. If you're using a caustic to clean your kegs, you're taking all that CO2 out. That gets replaced with air. Are you purging that keg when you're done? Are you purging it long enough? Typically you want to pressurize that keg as well and fill it under pressure. You don't want any turbulence. You don't want that keg to foam during filling. If you're filling upright, you're filling down the tube backwards, filling the bottom. And if you're in a larger brewery, you may fill the keg upside down. You fill backwards through the vent line. Like I said, laminar flow, no foaming. If you have excessive foaming during a fill that you need to purge out, something's not going right. And in this process here, again, if you have leaks, you have problems. Valve gaskets, keg coupler gaskets, they all need to be in good condition. If you're seeing beer weep out as you fill the keg, I guarantee you oxygen is getting in. So how do we measure oxygen? The current technology, state-of-the-art, is optical dissolved oxygen meters. It's not new technology. It's the most practical and it's relatively affordable. Low parts per million are very expensive, but you can't find a cheaper method than optical right now. Typically, the probe will go into your product. Machine will fire a laser at the membrane. Based on the color shift coming back, it'll give you the oxygen level. Like I said, ppm measurement for wort, they're pretty inexpensive, a couple $100. They get more expensive as you get into parts per billion measurement. Additional places you can put in inline sensors, and you can, if you buy an inline sensor, it's kind of fixed where it is. If you can get a portable analyzer like a Hawk 3600, or I know some of the Anton Par makes a couple of them now that are pretty effective. You can move those around. They'll clip onto a tri-clamp with a Zwickle, so you can move those around and spot check your process. And you can use those portable analyzers to do package oxygen. You pair that portable analyzer with a piercing device, you can punch a hole in a can or bottle cap and push the liquid out and measure it and see what's going on inside that bottle. There's one company I think that makes an optical sensor that actually shoots through the bottle to measure CO2 pressure. Pretty crazy technology, don't understand how it works. Target specifications. If you have the opportunity to measure these places, these are great numbers to shoot for. Bright beer tanks, less than 30 parts per billion. Like I said, you're coming off of fermentation close to zero. Yeast is taking everything up there. Packaged beer, total package oxygen should be less than 50 parts per billion, in my opinion. I do know some large breweries that are a little higher than that. I know InBev was a couple of years back there at 100 parts per billion, and that was only for their older fillers. Newer fillers are much lower than that. World class, less than 30 parts per billion. I have run small fillers, and we've achieved those numbers. It can be done. It's not rocket science. And lower is always better. Your job is never done. If you can reduce oxygen tomorrow, that's your job tomorrow. Just keep going. There's a slide I've seen before, and I actually found out who the guy who said this was. The race for quality has no finish line. So technically it's more like a death march. If you did a good job in oxygen management through your process, it's not perfect. There's always room to improve. The question is, how much time do you have to do that? What's going to cost you to do a better job? But your goal should always be to do better. And that's with anything in brewing. So dissolved oxygen versus total package oxygen. Dissolved oxygen is the amount of oxygen in the liquid. So there are a few ways to do that. You can, a piercing device will pierce the vessel, you'll push the beer out through the tube and go into the machine and measure it. Total package oxygen is a little bit more complicated. And that's really a true measurement of how good of a job you did packaging the beer. It includes the headspace. You can run a machine and fill very effectively and have no dissolved oxygen or very low dissolved oxygen in the package. If that headspace is full of air, you have problems. There are some people I've seen talk about shaking a can to get to TPO. Shaking is part of the process. It's not the whole process. Some people say, I shake my cans, so my DO is, I know my TPO is low. No, you don't, because you don't know how much headspace you have. To measure TPO, we require measuring headspace volume. If we have the shake and dissolve oxygen, we can actually use those two factors to calculate total package oxygen. I've seen breweries do a phenomenal job filling a can and a terrible job before they cap it. Everything looked great at the filler, but that air in the headspace is a problem. And think about it, oxygen doesn't like to go in liquid. We can't breathe underwater, oxygen doesn't go down there. There's still dissolved oxygen there. So the headspace is really critical. That's where most of your oxygen is going to live until it reacts with your beer. So there's companies that do direct measurement of TPO. Two that come to mind are Orbisphere, Hawk, and Anton Par, and they have some type of machine where you'll put a container in the machine will pierce the vessel. They may directly measure gas phase in the headspace, or they may shake the beer and measure dissolved oxygen after they've calculated headspace as well. You can do this with some low-level DO measurement and basic lab equipment and lots of math. Here's the formula. If you guys want to take notes, this is the important formula. Don't write it down. Don't even think about it. But there's spreadsheets you can do, and if you buy a dissolved oxygen meter from Hawk or Anton Par, they will send you a spreadsheet to do this math for you. It's pretty ugly looking math. Here's some work I did on this a few years ago. We would take a sample of 6 containers for testing in this brewery I was working with, and we'd take heads 1 through 6 off this particular machine, and we'd measure dissolved oxygen in that can. that was part of it. Then we take another can off the same head 1 through 6, and we measure shaken DO, and we get a picture there what's going on. And we'd also weigh the can, and we knew what the density of the beer was. We'd actually measure the volume of liquid in the can. We know how much the can holds, so we do the math. How much head space is really there. We know how much liquid is there. We know how much, we can take that can after it's empty, we can fill it with water and measure it, measure the weight, and measure the total volume. So we've got 355 milliliters of beer in there. The can may hold 360 mils, so you got 5 mils of head space. In this spreadsheet, I actually did a chart. It's on the back page of the spreadsheet that we went through, and we had standardized measurements of the headspace volumes of every can we used from every supplier, every bottle we used from every supplier. Even cans are very consistent. You'll see a little variation in bottle fill levels, but it's close enough for what we're doing. So in this process, we do shaken and unshaken. We measure the volume of the liquid. You can see we've got can fill levels over in the middle here. And these were cans, 12-ounce cans in this case. And there's the fill levels for our cans, 12.01 ounces, 11.98 ounces. And we averaged 11.995 ounces in the sample. So it's pretty good. With those numbers, using that formula I showed you before, we wind up with this output over here on this side. On the green column here, we get our total package oxygen, which was a measurement of the dissolved oxygen equilibrated with the headspace, and based on the shaken can, we know how much oxygen was in the liquid. We know how much oxygen likes to go to the headspace, and we can back calculate that out. In this case, we take our TPO average. We look at our, how much oxygen in our process, which we'd measure at the base of the filler coming in, and versus how much was in the can coming out. So in this case, this brewery, this was 2010 maybe. We were looking at 130 parts per billion of total package oxygen in this case. And we were seeing that during the packaging process, we were picking up 86 parts per billion. So there's an opportunity. How can we manage our filler better? How can we make sure we're getting enough purging, that we're getting enough pre-evacuation if we're doing bottles? And we'd say, okay, how much inline? We'd measure the tank before we packaged. We'd measure the base of the filler, how much inline pickup. In this case, we were picking up 4 parts per billion. If we saw that number spike, we'd go look at our hoses. Are there any leaks? We'd look at our pumps. Are there any leaks? That's where problems are going to be. And we found that packaging during the pickup process, we were picking up 62% of our oxygen. Okay. We'd look at our filler pickup, which was quite low. And then we would look at average headspace pickup. In this case, our headspace was 40 parts per billion. So in this case, we go back and say, okay, what can we do to manage our filling process? Can we do that more gently? Are we getting nice cans coming off, they're not foaming? And then we look at that. And if you see that headspace, we go back and look at the seamer. Are the cans not traveling the seamer fast enough? Are they not getting enough undercover gas? Things like that. So we color-coded the output in this case. Each one of these things means something. Inline pickup, filler pickup, headspace pickup, and total packaging pickup. So it kind of broke it down where we need to go look for these problems. But this requires one of those fancy TPO machines or just a low-level dissolved oxygen meter. So oxidation chemistry, radical reactions that happen in free radicals in beer, metal, things like copper and iron accelerate oxidation. Copper and iron are responsible for Haber-Weiss reactions and Fenton's reactions, which will pull oxygen out of your water in the product and break things down, oxidize, and continue to oxidize more beer. Not a good thing. I know breweries that have had issues with oxygen pickup from malt suppliers, things like that. I've seen higher levels of metal pickup in filter powder if that's not bought the right grade. And then, if you're really curious about that, if you look on the New York State Brewers Association, website. I did a presentation on trace minerals and brewing in 2024. Things that happen that we don't like to see are Strecker degradation. We'll see reactions of malt compounds that will go to staling in beer. It's not trans-not but it's other flavors that taste like stale beer. And that process starts early on with your maltster in roasted malts, things like that. Things that we don't like to see these days, we're all making IPAs, hop oxidation, terpenes and thiols. You know, terpenes are the wonderful aromatics that we open the bag of hops up and smell. Thiols are things that we break loose in fermentation. There are some brewery yeast suppliers that sell yeast that's been modified to produce more thiols than regular yeast. And some will tell you that you have to buy their yeast. It's the only way. That's not true. These are natural genes that they've inserted copies of. They do exist in traditional brewing yeast, different levels, different places. Sensory impacts of oxidation, muted hop aromas. You know, terpenes, you'll lose that hop aroma. You think things like myrcene, linalool, geraniol, and you know they're wonderful, pleasant aromatics that we want to see in our product. And if we oxidize them and stick an oxygen on that molecule, they become heavy, and they're not aromatic, they're not volatile, so we can't smell them. Thiols are sulfur compounds. You know, we see these products at very low levels, and they're very effective in carrying some wonderful fruity aromas to our beer. But they are sulfur compounds. People are very sensitive to sulfur compounds. We're talking about, you know, parts per million, parts per billion, and some hop components. If people can identify and notice sulfur compounds in parts per trillion, so it's a different level. And people who have lots and lots of these thiols in their beer, those are sensitive things as well. If they oxidize, they become unpleasant, in my opinion. They tend to go towards burnt match. You get a sharp sulfur aroma from them. There was a brewery a few years ago that I know did a product that was available in cans and kegs. The beer was wonderful on draft. They had oxygen problems in packaging. Canned beer smelled like burnt matches. Cardboard flavors, trans 2 not at all. Unpleasant thing. If you're making a light lager without a big hop profile, you may see this first. And like I said, color darkening, sherry notes, these are high levels. These are really, somebody's had a really bad day in the brew house and a really terrible day in packaging. And I get phone calls from people with these problems. You know, what happened to my beer? It's much darker a week later. Something's going on in the can. No? You put bad things in the can with the beer, oxygen. Nobody calls me the day after they made a good decision. Trust me. It's always after they've done something horribly wrong and they've spent all their money. So hop aromatics, a few years back, I looked at concentration of aromatics using a GCMS. You know, we looked at 17 of our most prominent hop aromatics in our beer. A lot of these are simple things that we're used to. Myrcene, linalool, caryophyllene, the big components, pinene. But there's a whole bunch of fractions in here that are all very important to our process. We looked at this over 37 different varieties, and you can see some varieties were very high in levels, and then you know some of these are actually duplicates. We have the same hop variety in here twice from two different farmers. It can be quite different. You know, each color band in here is a different aromatic. So I was working at a brewery a while back and to really understand this, and then to kind of push the packaging team to do a better job in packaging, explain to them how important oxygen was. You know, they don't want to hear from a quality guy about that. But you put numbers in front of people, you get their attention. So we took a beer here. This is an IPA that we produced. We looked at tank oxygen level. We were at 31 parts per billion in the tank. We measured the base of the filler, 35 parts per billion. Pretty good. We didn't pick up much there on the way to the filler. The tank was okay. The filler was pretty good. So then we looked at, how much do we pick up through the filler? We took those samples off and did dissolved oxygen measurements. And we got one anomaly at 25 parts per billion. Maybe some of that oxygen escaped in the process and the shearing. But we'd see a little bit of pickup during the filling process. But look at the headspace numbers. Headspace was a big part of this. So we found, we ran the same beer during the same run. And I had the operator manipulate the filler. We turned the speed up, we shortened the purging cycles, And we went from 118 parts per billion of total packaged oxygen to 270 just by running the filler faster with less control. What did that mean to the beer? Well, when you're looking at your beer, you can take stuff off the filler. That doesn't tell you too much because the damage hasn't been done. We took this product and we waited 3 weeks. We figured, hey, it's going to sit in the warehouse for a week or two. It's going to go to the distributor. Yeah, as soon as the consumer is going to see this product, it's probably 3 or 4 weeks. So we waited 3 weeks and measured it. And look at these numbers here. This is the percent reduction in hop aromas. Myrcene down 78%. Linalool down 59%. D-limonene, that pleasant citrus character, down 97%. Pinene, that fresh pine character you get out of things like Chinook, down 95.1%. Caryophyllene, a nice aroma that kind of goes woody, cedar-like. And these were the biggest ones we had in our stack back here. We just picked the biggest ones to work with. And we found that overall we lost about 73% of our hop aroma in 3 weeks. Who here has the luxury of having all your beer consumed within 2 or 3 weeks? Didn't think so. And the variation in the hop aromas here shows you how reactive are. Some products react very quickly. Myrcene 78%, D-limonene 97%, beta-pinene 95%. Those are very reactive things. The humulene was a 38% reduction, caryophyllene was 17%. Those were less reactive. They reacted slower. So some things are more sensitive than others. So thiols, everybody's all geeked out about yeast that's been modified to produce thiols. Sulfur compounds. Like I said, humans can detect sulfur compounds in parts per trillion. Thiols can oxidize and produce burnt match aromas, among other things. Like I said, the brewery I mentioned before, they did a great job. Their draft beer was amazing. Lots of fruit. The can, not so much. It smelled like burnt matches. So, this example here, that 73% reduction, that's 150 parts per billion. Who can visualize 150 parts per billion? It's pretty tough. So I did some math. You got ChatGPT these days. Had to make some corrections. Take a long distance measurement between Albany, New York, and San Francisco. Straight line flying distance is 2,560 miles, 4,100 kilometers. 150 parts per billion of that journey. We translated that to kilometers, meters, then broke it down to feet. That's 2 feet of that journey. So we're worried about that much of a trip to San Francisco impacting our hop aroma that much. So we're talking about pretty minuscule amounts. Little things really matter here. So 2.03 feet. Unfortunately, it's an expensive meter to measure things that small, but it's important. If you're making a significant investment in canning, bottling, start to plan for this expense as well. So what's sensitive? Hoppy beers are very sensitive. We've got lots of these aromatics that obviously can disappear very quickly. Light lagers are vulnerable. I think the selling reactions are pretty obvious in these. If you have a Pilsner, Helles, Kolsch with oxidation, you're going to lose some hop aroma, but your biggest loss, in my experience, tends to be that stale, papery character. Strecker degradation, that beer stale character. Dark beers seem to be a little bit better at masking some of these. Dark beers also mask hop aromas too. But these things do matter. And dark malts can also be a source of iron pickup. There was one maltster who was actually here this week. A few years back, they were disqualified as a supplier from a large brewery because their roasted malts had a high iron content. Well, they upgraded. They don't have that problem anymore. But the more you handle malt, the more opportunities there are to pick things up in it. So what can we do? Start in the brew house. Oxygen impact is cumulative through the brewing process and packaging. Packaging is the most important, obviously, Beer is much more sensitive than wort. Make sure you have CO2 purging SOPs, do closed transfers, and fill gently. Don't splash your wort around, don't splash your beer around. And do audits, watch your process. If you've got a team, or if you have another brewer nearby that can help you and let you borrow a meter or come over and help you out and take some measurements, do it. Measure what you can, make improvements, and repeat. Jim McDermott did a talk on control charts 2 hours ago. I got into doing control charts, looking at package oxygen levels. It's a great way to measurement. You whip out a chart at the packaging meeting and say, here, your process is out of control. Those guys would lose their minds. But it's true. They could put beer in bottles and cans very effectively, but if they weren't doing it in control and consistently in managing oxygen, it was a problem. So routine DO checks are important. Start with wort, look at filtration, bright beer tanks, total package oxygen is kind of the end goal. It's a more expensive part of this process. Sensory panels, taste your beer. Taste it in market conditions. Try it a few weeks old. Try it stored warm. Try it stored cold. And see, can we afford to store our beer warm before you do it? You take the best care of your beer in-house. What happens to it once it leaves? Do a shelf life study. Put a 6-pack of your beer on the shelf. Take a can off the shelf every 2 weeks. At what point does it not taste like your beer? Where do you want to put your shelf life? And the answer is different. All these things we talked about, from mashing in to packaging, impact that number. More people call me and say, hey, what's my shelf life? I don't know. I don't know if you're doing a good job in the brew house. I don't know if you're doing a good job in packaging. You can give me a little bit of data, but it really comes down to how it tastes in market conditions. There's a gentleman here, actually he's not here today. He's a brewer, and he was talking about the judging of beer, and he said his beer never judged well. There must be something wrong with the judges. That was 5 years ago. I said, have you tried your beer 3 weeks old, hand bottled? Well, no. Well, guess what? That's what the judges are trying. I never thought about that, he said. So, taste your beer as your consumer sees it. Out of the bright tank, it's great. Right off the filler, it's great. But is your process good enough to hold up in the shelf life department later on? So, what you can do, control oxygen at all stages. Fermentation is the only place you want oxygen in your process, and you need to manage that. Don't use too much, use the right amount. Packaging is the most critical point in this process, and measurement drives quality. If you can't measure it, you can't control it. Any questions? I'll be around for a little bit this afternoon. My email's up here if you guys want to email any questions, and I'll show up and talk about beer anywhere.
I have a question. Thank you. First of all, I was surprised you didn't put Ryan Demler's email up there to send emails.
Yeah, there's a guy who shows up every year now and puts my email to answer questions for his presentations. He's not here yet this year.
Ryan Demler at communityworks.com. Email questions. You had mentioned the effects of wort aeration on 4VG production in wheat beers, and so you were suggesting to under aerate or aerate less in those beers.
Yes.
To promote 4VG?
4VG is that clovey, spicy character we see in wheat beers. In my current world, we see it in rye whiskey. By lowering oxygen levels, you'll see more 4VG production. It goes
Or I guess increase it if you want to lower the 4VG.
Yeah, you can manage that as a process, and it's typically less than you'll see in your regular beers. And that goes through yeast taking up frulic acid, that whole life cycle there.
And my second question was, you mentioned some stuff about sheet filters and plate and frame filters, what do you want to call it? Which I think I might be the only person in the room who still uses one. Did you ever? Hey, thank you.
You filter?
I know. Well,
I spent 8 years.
It's the old guys who raise their hands on the filters.
I spent 8 years in a project making beer clearer for a larger brewery years ago. Like, nobody cares.
Yeah. Did you ever do any DO measurements on the in and out of that sort of process and see? Because like you said, things leak out, oxygen leaks in, and they are notorious for leaking beer out. And see any significant pickup of oxygen across the flow of a sheet filter?
Best practices were to use low oxygen water to set the
Yeah,
filter
deaerated
up.
water.
And
Yeah.
it could be boiled water.
Yeah.
It could be heat sterilizing.
And that would be better than just purging with with gas.
Yes,
Okay.
because that you'll
It
drive
gets into
all,
the conduction
yeah,
craning.
you'll drive all the gas in and heat your sterilizing agent at that point.
Okay.
And you can heat it overnight.
Let it cool down over.
Yeah.
Okay. That's more effective than just purging out chemical sanitizer.
In my opinion, yes.
Okay.
And also make sure you crank that wheel as tight as you can.
Yeah, you keep the dripping to a minimum as much as you can.
Yep.
I've always wanted to put a DO meter on in the out of my filter and just look and see, can I see it, pick up across it? Because there's a lot of anecdotal talk about from people who use them about seeing shorter shelf life or oxidation of IPAs or things like that.
I know there's pickup. I don't have much experience
Okay.
quantifying on that, but yeah, the tighter you can pack it.
Andy does. Okay.
Yeah, it wasn't nearly as bad as I thought it would be.
Yeah.
So the few times I've done it, it was like 15 in, 35 out, something like that.
Okay.
And I was expecting far worse than that.
Yeah, I mean, 23 years I've been using one of those in some form or another. So anecdotally, it would tell me that if I had massive oxidation problems, that would be a source. But
You
then
know
being
by
able to measure it is different, right? So
you know by tasting it.
yeah.
But putting a number on it.
But I'm also a brew pub brewer. My beer's been sitting out there for 6 months.
Yeah.
So. Other people have questions besides me? I'm sure there's a lot of other smarter people in the room than I am. No? All right. Well,
guess I have
thank
all
you,
the
Rich. Appreciate it. Well, you answered so many questions that no one has any questions about. Thank you all very much. And,